So welcome to the seventh week of the discussion session of the course Strength of Material course offered by NPTEL. The course instructor of this course is Professor Siman Kumar Bhattacharya. He is a professor from IIT Kharagpur. Myself, Asif Raza, I am the teaching assistant of this course. I am a PhD scholar from Department of Civil Engineering, ISC Bangalore. So since seventh assignment is already out, its due date is also over, and yeah, so we can discuss questions, uh, direct questions of the assignment number 7. So in the first half, we'll be discussing assignment number 7, and further we'll discuss more questions relevant to assignment number 7, so that might help you in the final exam. So let's start. So before that, something to tell. Uh, so for the bending moment diagram case, the sign convention which we normally follow is this, where this is the sagging moment, and this is hugging moment. So this says that if you come, like if you take the case of sagging moment, and if you are following, trying to find the bending moment from the left hand side, then the anti-clockwise would give you the positive sagging moment, and likewise if you come from the right hand side, the clockwise moment would give you the sagging moment, and that is normally taken as a positive. Vice versa regarding hogging moment. For the shear force, uh, um, so we take this as the positive sign convention, the negative we take this. Okay, so this thing is the most basic thing which is required for this assignment. Few more things to add. I'll just tell this. Yeah. So regarding supports, or rather, I'll just keep different structure. I'll provide you. So first thing first. Uh, is it not visible? Yeah. Okay. So next is regarding supports, or I'll just take special beams which are normally used. So first one is simply supported beam. Uh, Normally it's like this. And reactions which are there in this case is this. I'll just take this as RA, RB, and one horizontal reaction HA. Okay. Now the second one is cantilever beam. Let me draw this. Okay, so in this reaction would be RA, HA, and moment MA in this. Next one is fixed beam, and that would be fixed at both ends. So reactions RA, RB, HA, HB, or this one also has HB, then MA, MB. Okay, this the simple one. If you don't want to think much, you just focus on the type of supports. So in the simply supported beam, you can see there's a pin joint here. At the pin joint, there's one vertical reaction and there is one horizontal reaction. While in roller support, there is only one vertical reaction. Rest of the things are zero. uh, and the one more support is fixed support. At fixed support, all the three reactions are there: the vertical, horizontal, as well as the moment. And in the free end, there isn't any reactions. Okay, so this is what you can keep this in the mind for solving the problem. Okay, now let's start discussing the questions, and I would expect you to give quick answers because the assignment solution is also already out. Okay, let's start. The first question is, pick the incorrect statement from the following, and the options are: option A, load intensity on a beam is the first derivative of the bending moment. Option B, if there is no shear, the bending moment is constant. Option C, at the location of a concentrated load, there is a change in the rate of change of bending moment. And option D, at the location of concentrated moment, there is a change in bending moment. So you can give your answer in the chat box itself. So what is the incorrect statement out of all these four? Yeah, Raj, you can give your answer. Yeah. Yes, so correct answer is option A, which is the incorrect statement out of all these four. So the correct statement pertaining to the option A is this. It says load intensity on a beam is the first derivative of the bending moment. So either the statement can be like changed into or I'll just write it dv by dx is equal to minus q, or dm d square m by dx square is equal to minus q. Okay, so if you see the correct thing from the rectify it, either the statement should be the load intensity on a beam is the second derivative of the bending moment, that is this, or the load intensity on a beam is the first derivative of the shear force. So the corrections that can be done is like either here or either here. Yeah. Okay. So option B says if there is no shear, the bending moment is constant. Yeah. So regarding statement B, um, so we have a relation. V is um, shear force V is equal to dm by dx. So if there is no shear, that is V is equal to 0, uh, that would imply dm by dx is equal to 0, and this would imply that m is some constant. So option B is the correct. Option C, at the location of a concentrated load, there is a change in the rate of change of bending moment. So that is also correct. And the last statement, at the location of concentrated moment, there is a change in bending moment. So that is also correct. Okay, moving on to the next question. In a beam with transverse loading, the point of contraflexures occurs at a section where options are: option A, bending moment is minimum; option B, shear force is maximum; option C, shear force is 0; and option D, bending moment is 0. Yeah, Raj, you can give your answer. So you just want so in the beam, the point of contraflexure occurs at a section where, yeah. So yes, option D, bending moment is 0. So if you observe the uh, statement itself, this is like contraflexure. Flexure implies bending, and contra means kind of a contradictory thing. So the point of contraflexure is at that point where my bending moment changes its sign, like either from positive to negative or negative to positive. So that would occur when my bending moment is 0. Okay. So yeah, we got it correct. Uh, Moving on to the next question. If the bending moment diagram BMD of a beam is a right angle triangle with the span of the beam as its base, then the beam is A, and options are: A, simply supported beam with a uniformly distributed load over the entire span; option B, a cantilever beam with a uniformly distributed load over the entire span; option C, simply supported beam with concentrated load at the free end; and option D, cantilever beam with concentrated load at the free end. Okay, so rather asking like the correct option directly, we can like work around this all these four options so that we have a better picture. Okay, so first is simply supported beam with a uniformly distributed load over the entire span, and that is just let me draw this. So UDL is kind of, if this is kind of W, kilonewton per meter, and this is L. So what is if you know what is the BMD for this bending moment diagram for this simply supported beam? Do you know? Yeah, Raj. Uh, do you know what kind of BMD pertaining to this option A structure? Okay, I'll help you. It's a parabolic structure, and at L by 2, it is equal to W L square by 8. You're giving option B as the answer. Okay, let's see. So this is parabolic. Now, let's see option B. Option B is cantilever beam with a UDL over the entire span. That is, let me draw this. and this is L and UDL this. Okay, so pertaining to this, my BMT would be, let me draw the span first. Yeah, so W uh, W like at any section, if I take this as X, so at any section my BMT would be equal to Wx times x by 2. That would give me kind of Wx square by 2. Okay, and this would be kind of going to the negative part, and this would be equal to yeah, BMT would be, this would also be a parabolic, or rather quadratic, whatever. So this would be equal to W L square by 2. Okay, positive, negative. Now the C. So as you were saying, option B, I don't think the correct answer would be option B, because this won't be right angle triangle. It's a quadratic. It's a quadratic or parabolic. Okay. Now let's see option C. Simply supported beam with a concentrated load at the free end. Okay. So simply supported beam. Let me draw it properly. Simply supported beam with concentrated load at the free end. Oh, the question is wrong, I think. Simply supported beam with concentrated load at the free end. I think it should be uh, uh, a roller side, or roller at the roller support. Okay, because there's no free end or something like that. So if I take like saying the simply supported beam with concentrated load at the roller support, that is like this. If the W kilonewton acts, so what would be my BMD, bending moment diagram? It would be 0 all throughout, because the reaction in this case, it would be kind of W here, and here it would be 0. So this will cancel out each other, and all throughout the section it would be the bending moment would be 0. Now let's see option D. And the option D is cantilever beam with concentrated load at the free end. Uh, with concentrated load at the free end W, and if I take this as L, yeah. So in this case, my bending moment diagram would be, see, at any section, like from X, the bending moment would be equal to what? W times X. W times X, right? At any section. So this would give me like like if I start from the right hand side, at x equal to 0 it would be 0, and at the left hand that x would be equal to L, that would make this as WL, and this as get it. So if you so these are like bending moment diagram pertaining to all the structures provided. Now let's see what is the question asking. If the bending moment diagram of a beam is a right angle triangle with the span of beam as its base, then the beam is a. So if you see all the four options, out of all the four options, the one which is having bending moment diagram as a right angle triangle is the fourth one. See, this would be the fourth right angle triangle, and the span of the beam itself is the base of this right angle triangle. So correct answer is option D. Okay, I hope I have given a with explanation that would help you. Okay, moving on to the next question. Before that, like I would ask you to give confirmation whether you understood or not in this regard. This is clear, right, Raj? Are you there? I cannot hear you if you are speaking. You can write it in the chat box if needed. Okay. Okay, moving on to the next question. So question 4 is the maximum bending moment in kilonewton meter in a simply supported beam of 4 meter span subjected to uniformly distributed load of 10 kilonewton meter inclusive of its weight over the entire span is. Okay, I just told you about this regarding this option A. If you see, this is the same thing which has been asked. So in this, like if you see, when a simply supported beam with a UDL uniformly distributed load is applied over the entire span, the bending moment diagram comes out to be a parabolic structure with the maximum bending moment at the center as WL square by 8. We just need to use this here. So if you can just see first, write the thing first that the entire span or the span of this beam is 4 meter, and the UDL in the uniformly distributed load is given to be 10 kilonewton per meter. So the bending moment, that maximum bending moment would be WL square by 8, and just substitute this. Substitute it should be equal to 10 into 4 square by 8. So this would be kind of 4 for 16, 160 upon 8, that would be like 20 kilonewton meter, because W is in kilonewton per meter and we are multiplying it with meter square. So correct answer would be option C. Okay, I think this is the most easy one. Uh, Moving on to the next question. Like if you feel anywhere like doubt, you can write it in the chat box, or ask, unmute yourself and ask. Okay. Moving on to the next question. Yeah. So question number 5. A simply supported beam AB of span 6 meter carries two concentrated transverse loads 5 kilonewton each at 2 meter from A and B respectively. What is the shear force in the middle 1/3 portion of the beam? Okay. Yeah, first thing first, uh, let me help you in drawing the structure. So this is a simply supported beam. This is A, this is B. Uh, Total length is 6 meter. A, B. Then 5 kilonewton a load is applied at 2 meter from A and B respectively, and that is uh, like 5 kilonewton, 5 kilonewton. Okay, so this is what is given in the question. We need to find what would be the shear in this middle uh, one third portion of the beam. So for this, let us draw the shear force diagram. Okay. Uh, so first thing first, what would be the reactions at the supports? Let's draw this. R A, R B, H A. Okay. Now using sigma Fx is equal to 0, this would give me H equal to 0, and take then let us take moment about A equal to 0. This would give me RB times 6 minus 5 into 4 minus 5 into 2 equal to 0. This would give me RB is 5 for the 20, 30, 30 by 6, 5 kilonewton. Now take the last one like Fy equal to 0. This would be like Ra plus Rb is equal to 5 plus 5, and Rb is equal to 5. Just substituted, then Ra would also come out to be 5 kilonewton. Okay. Now let us draw the SFD shear force diagram. So it will come out to be since structure is now like 5 here, 5 here, 5 here, and 5 here. Okay, so for this my shear force diagram would be so right side upward 5, so it should be like this. Then till here it should be like this. Let me check it. Sign convention which I said. Yeah, so this is this. Okay, so right side upward positive, so this is 5. Then again it at this point it comes out to be some part of it is a negative, so 5 minus 5 it will make this thing as 0. Then again we'll traverse to this, then again it would be will reach here, it would still be 0. Then as soon as we move more towards left, so we'll go towards down, like minus 5 will come out, then again like this. Okay, so this is what would be the shear force diagram. So if you see now, the middle uh, one third portion, like is the question is asking, this is the shear force is equal to 0 in this middle one third portion. So correct answer would be option B. It's 0. Okay. So if the question had been like, what is um, shear force in the left or right one third of it, it would be 5 kilonewton. Okay, the magnitude is 5 kilonewton. So then the option would have been option D, but in the current case it would be option B, 0. Okay, uh, moving on to the next question now. So question number 6, for the simply supported beam shown in the figure, at what distance from the support A will the shear force be 0? Uh, so directly saying what would be the shear force be 0, I'll just ask you step by step. Okay, so first thing first, the reactions. The reactions would be RA, RB, and HA here. Okay, so what would be HA? Raj, you can say anytime. What would be HA? You can just use this. Sigma fx is equal to 0. That would imply HA equal to 0 because there are no other horizontal forces. So HA would be, like, consequently it would be equal to 0. Uh, mm, okay, now let us take moment B, like summation with respect summation of moment from the point B equal to 0. So this would be equal to what? RA times L minus the load itself. The load would be equal to what? Half into W into L, and it would act at a distance. It would act at a distance L by 3 from the right hand side, and we'll just substitute it here. L by 3 equal to 0. So this would give me RA equal to LL cancels out. It would be equal to W L by 6. Okay. Yeah. If you want to complete the thing, take sigma Fy equal to 0, that would give me R RA plus RB equal to WL by 2, and this would give me RB as WL by 2 minus WL by 6. This would be equal to 3 to WL by 3. Now, what is the question asking? For the simply supported beam shown in the figure, at what distance from the support A will the shear force be 0? So, let us take that section the x from left hand side. Okay. Now, moment at x is equal to what? RA times x minus RA times x due to the reaction support, and support reaction, and uh, the other one, the external load which is acting. So at the mm, at this point, what would be my this maximum load? Like at this point, what would be the this load equal to? So all throughout, it's like the maximum point is W for L, right? So for X, it would be equal to W by L times X. Okay. Mm, so that would be like W by L times X times now since it's a uniformly varying load, we just need to multiply it with 1 by 2 times x, and it will act the like the we can convert this uniformly varying load to a concentrated, and it will act at x by 3 from here. Okay, so x by 3, and okay. I'm making a mistake here. The question is asking about shear force, and I'm finding moment. So we can just do one thing. I can take this one out as we can take this as a shear force. We will just remove this and this. Okay, and make it 0. So we have R A equal to W x square by 2L. Wx square by 2L, and this would give me x as root over 2 R A L upon W. Now let's substitute what is RA. RA is WL by 6 on W. W cancel out. This would give me L square by 3 root. This would imply L will come out to be L by root 3. Okay, so the correct answer is option D, L by root 3. Okay, moving on to the next question. Question number 7 is a simply supported beam AB is subjected to a concentrated load at C at the center of the span. The area of shear force diagram from A to C will give, and options are bending moment at C, option B shear force at C, option C difference between bending moment values at A and C, and option D is both A and C. Okay, so let's draw the diagram first. A simply supported beam is subjected to a concentrated load. Simply supported. Simply supported beam AB is subjected to a concentrated loads at C at the center of the span, and that is like this. I'll just give this as capital W, and if it is L here, this would be L by 2. I'll just write this L by 2. Okay. So the area of shear force diagram from A to C will give. Okay. We'll do something regarding this as first thing first. We'll draw the SFD or BMD. So if you solve this, RA RB HA. So sigma fx would equal to 0 would give me h equal to 0, and then using sigma fy equal to 0 and sigma m equal to 0, this would give me RA and RB is equal to W by 2, because it's a symmetric uh, as in the loading case. So RA/RB would equal to W by 2. So so shear force diagram SFT would be kind of if I take right side upward positive, this would be like this, and then this. Okay, the W by 2, W by 2, and bending moment diagram is one thing we can do is then bending moment diagram would be W by 2 or times L by 2. This would be kind of WL by 4, and then this is equal to WL by 4. Okay, and this is at C. A, B, and A, B. Now the question is area of shear force diagram from A to C, and that is equal to WL by 4. If you see area of shear force diagram from A to C equal to W by 2 times L by 2, that is WL by 4. Okay, and this is like if you see bending moment at C, bending moment at C is WL by 4. So this would be kind of, yeah, area of shear force diagram is equal to the bending moment value at C. So that is correct in this aspect. Let's see what is shear force at C. Shear force at C, if you take at the left hand side, it is minus W by 2, and if you take on the right hand side, it's W by 2. So that won't be the case. Difference between bending moment values at A and C, that is MC minus MA, and since MA is equal to 0, this would be equal to MC, and that is WL by 4. So if you see, this is also correct, this is also correct, like it's equal to this. So correct answer would be option D, both A and C. Okay. So I hope this is clear. Moving on to the next question. The following beam is subjected to a concentrated load of 25 kilonewton at B and a clockwise couple of 120 kilonewton at C. Find the vertical reaction at A. Okay, just need to find what is the reaction at A. Okay, first thing first, let's draw it separately. So 25 kilonewton is acting here. A, B, 4, then clockwise 120 kilonewton meter, 2 into B, C, D. Okay, so need to find the vertical reaction at A. Reactions developing it would be RA, HA and RT. Now first thing first, just take this fx is equal to 0. This would imply HA is equal to 0. Now to find the vertical reaction at A, we just take summation of moment about D equal to 0. So this would be equal to RA times 4 plus 2 plus 2, that is 8 minus 25 and then plus 120. Oh sorry, 25 into 4 plus 120, because we're talking about clockwise. We'll take clockwise here, right? And this is equal to 0. So let's correct it properly. So RA times 8, it would be kind of 20. Then this would give RA is equal to 20 by 8, and this is 5 by 2. This is give me 2.5 kilonewton. Yeah, correct answer would be option A, 2.5 kilonewton. Okay, moving on to the next question. A simply supported beam AB of 6 meters span is carrying a UDL of 5 kilonewton meter over a length of 3 meter from the right support. Pick the correct shear force diagram from the following. Okay. Yeah. So without actually solving the this problem, we can like uh, check from the options itself whether which would be correct. Okay. So if you see, we can directly see that the reactions at RA would be equal to, like if you see, so reactions at RA would be equal to 3.75 kilonewton, and reaction at RB it would be equal to 7.25 kilonewton. Okay, now 11.25, then 5 kilonewton per meter. Like if I come from, if I draw the shear force diagram from the right hand side, okay, so RB is equal to 11.25 and 5 kilonewton per meter, that UDL would act opposite to this. Okay, so 11.25 minus 5x, so this would linearly decrease it, right? And this would decrease it till where? This 3 meter, till the center. Okay, and kind of 11.25 minus 5 into till the center, it would be 3, 5 is 15 minus, so this would be around minus 3.75. So kind of the sign would completely change and the value would be around 3.75, and it's a linearly varying shear force diagram. So out of the all four options, like mm, let's see, what I have speculated about this is, if you see option A here, it says there's a constant, it doesn't vary too much, and this won't happen because it's a UDL. There's not something like there's no force in this. Okay, and this change directly says that there is a concentrated force only at this point, so that is not the case. Now if you see option C, uh, if you see this, so like there's a constant part here. This implies that there isn't any force here. This is like the reaction part force, then there is no force here, then again there's a UDL acting on this, and that is not the case in provided here. And so we can eliminate the same thing from for the D also. The correct answer would be option B, because as I told you, from the right point itself, there would be a linearly wiring kind of thing, and that's why like our correct answer would be option B. So without actually solving it, we can speculate which would be my correct answer. Okay, so correct answer is option B. Moving on to the next question. I'll just remove this page altogether. Yeah. Option question number 10. For the figure shown, the shear force and the bending moment at a section 3 meter from the left support A are uh, okay. So we need to find the shear force and bending moment at a section 3 meter from the left support A. Okay, let me draw this first. Load is uh, 10 kilonewton here and 15 kilonewton here. This is 1 meter, 5 meter, then 1 meter here. A, B, C, D. Okay, so we need to find from A 3 meter, right? That is, so if I take 3 meter from here, uh, that would give me like uh, 3 meter from right also. Okay, 3 meter from left. A B C D E, right? Okay, now uh, hmm, okay, so the reactions that would be produced here would be kind of RA, RB, and HA. Okay, I'll just try to find RB because if I solve if I solve SFT and BMD, if I try to find the shear and bending moment from the right hand side, only RB is sufficient to compute. So let's what I will do is I'll take moment about A equal to 0. So this would give me kind of 10 into 1 plus RB into 3, 5 minus 15 into 6. This is equal to 0. So RB would be equal to 15, 6, 90 minus 10. 80 divided by 5, this would be equal to 16 kilonewton. Okay. Now to find shear force at E. Shear force at E. So shear force at E would be kind of 15 minus RB. That would be like 15 minus 16 is equal to minus 1 kilonewton. Then moment at E is equal to 15 into distance is 3 minus RB into 2. That is 45 minus RB is 16 into 2, 32. 13 kilonewton meter. That would give me option C as the correct answer. Minus 1 and 30. Okay. Moving on to the next question. This is very good question. So let's solve this. The simply supported beam ABCD is loaded as shown in the figure. The cable passes over a small frictionless pulley at B and is attached at E to the end of the vertical arm. Calculate the bending moment M at section C, which is just to the left of the vertical arm. The options are 50.4, 36, 38.4, 30.4. Okay, so let me read the question once again. So we have a simply supported beam. There is a pulley attached here. There is a load W 27 kilonewton here. A, B, this is B, C, D, E. Okay, 2 meter this, 2 meter this, and 2 meter this. Yeah. Simply supported ABCD is loaded as shown in the figure. The cable passes over frictionless band is attached at E to the vertical arm. Calculate the bending moment M at section C. Okay, which is just to the left of the vertical arm. So we want to calculate bending moment at this point, right? This is 1.5 meter. Okay, so first thing first, reactions. So R A R D H A. So sigma fx equal to 0 would give me H A equal to 0. Now think now as the complete system as one thing. Okay, the reactions are only RA and RD now. So taking moment about T equal to 0 would give me RA into 6 minus W into 4 outside, this is equal to 0. RA would be equal to 2W by 3, and W is 27, right? So RA would be equal to 18 kilonewton. Okay. Yeah. So if you want to calculate RD also, that is RA plus RD is equal to W. This would give me RD is equal to 9 kilonewton. Okay. This is just an additional step, no worries. Okay. So reactions are done. No. The thing which we need to see now is this tension part, for which the reactions would be developing if I take this as a system now. Yeah, so in the pane now we have the reactions RA, that is 18 kilonewton here. There is a weight of 27 kilonewton is acting downwards, right? And the tension, there would be a tension here, tension. The tension develops. This is 27. And the direction is kind of this. So till here only I'll just draw this. Okay, this is C, this is A, this is B. Okay, we are given with this is as 1.5 and this as 2, right? Yeah. Now let's okay, so if I take this as theta, what would be my cos theta? Cos theta would be 2 by 2 square plus 1.5 square, and sin theta would be 1.5 by 2 square plus 1.5 square. Let me see if this gives me anything solid. Plus 1.5. Yeah, so cos theta would be 2 by 2.5, that would be equal to something, and theta would be 1.5 by 2.5. So 2 divided by 2.5 is 0.8, and 1.5 divided by 2.5, this is 0.6. Okay, now let's what do we need to calculate? Bending moment at C, which is just to the left of the vertical arm. So to calculate bending moment at C, right, from the left hand side, it would be kind of 18. This length is also 2 meter, right? Yeah. So 18 would act at 4 meter minus 27 into 2. Then if you see this the tension 27, it will be having like cos theta cosine component that would be acting along this uh, beam, while 27 sine theta it would be acting uh, perpendicular to it, so that would produce uh, along this that would produce moment. So I'll just write 27 sine theta into, that would be 2, and I'll just write it okay, equal to, oh so we need to calculate this thing only, so let's calculate it. So 18 for 72 minus 54, 27 sine theta, 27 sine theta is uh, um, 0.6, so 54 into 0.6. Let's calculate this thing. And then with this 72 minus 54 plus 54 into 0.6. This comes out to be 50.4 kilonewton meter. Okay. The correct answer is option A, 50.4 kilonewton meter. Okay. Solving the last question of the assignment number 7. Then we'll be solving questions, more questions. Okay, so let's do this quickly. The question is, a cantilever beam is subjected to distributed load as shown in the figure. The shear force V and bending moment M at the fixed end of the beam are. So we need to calculate the shear force and bending moment M of the given cantilever beam. Okay, uh, let's calculate it. Like, what would be my shear force at A and bend moment at A? So shear force at A, I'll just take this as A, this as B. Okay. So shear force at A, now A, B, C and D I take it. So the contribution of shear force from dB part, it would be kind of 1 by 2 into the weight, the maximum is 3 and the span is 1. Okay, so this is from dB section. Now from CD section, it's a UDL, so it would be 3 into 3, and from the AC section, so it's a we can like do this in the two way, either take it as a trapezium type, or you can uh, like sum it up as a rectangle and triangle. So what I will do is I'll take the trapezium way now. So for the trapezium, it is half into sum of parallel sides, and that would be 5 plus 3 into 1. Okay, so this would be equal to, let's calculate it, this would be 1.5, this would be 9, and this would be 4. So 9 4 13, 14.5 kilonewton would be my shear force at A. For the bending moment M. Okay, the bending moment at M, uh, from the dB section, it would be 1 by 2 into 3 into 1 times, that will act from here it would be kind of 1 by 3 from this side. So total it would be 4 plus 1 by 3. Okay. 4 plus 1 by 3. Okay. So this is from BD part. Now let's see from CD part. So it would be 3 by 3 into 1 plus 3 by 2. That would be 1.5. Now for the AC part, to calculate bending moment, I will take it as a sum of the as a uh, rectangular section and the triangular section to calculate the bending moment. So let me do that. So plus first from the rectangular part, so it would be 3 into 1 and distance would be 0.5, 1 by 2. Okay, plus now from the triangular part it would be half into base is 1 into height is 5 minus 3, that is 2, and the distance it would be acting as 1 by 3 from the left hand side. So okay, 1 by 3. Let's just calculate this and be done with this. So moment is 1.5 into 4. 4th is at 12, 13 by 3. Okay, 3 by 2, 13 by 3 plus 9 into 2.5 plus 1.5 plus 1 by 3. This is 13 by 2. This would be like 6.5. 9 into 2.5 is 22.5. 1.5 plus 0.33. This would be equal to, let's calculate it, 6.5 plus 1.5 plus 30.83 moment at a. So let's see. Did I make any mistake? Shear force is correct. Let me see the bending moment. Okay, half into base into height, half into base into height from the dp part, half into 3 into 1, that is okay. Then 3 plus 1 4 and 4 plus 1 by 3, this is okay. Now this is from the CD, 3 into 3 and the distance is 3 by 2, that is 1.5. So 1 plus 1.5, that is okay. Now okay, if in the for the trapezoidal part, 3 into 1 into 0.5, that is also okay. Now this one, 5 minus 3, this is 2, right? So half into 1 into 2, 1 by 3. This is also correct. Yeah. Did I make any mistake? 3 by 2 into 13 by 3, right? 4 3 is 12 plus 1 13 by 3, 3 is 9 into 2.5 and 3 into 0.5, then 1 by 3, 13 by 2 6.5, 9 2 is 18, 9 5 yeah 45, for 22.5, 1.5.33. So 30.83 is what is coming. Let me check. Three into 4, why is this 3 into 4 into 2? It's best to check this one because I think correct answer would be out of all the options, this none. The correct answer should be 14.5 and 30.83, because if I just take this, the middle portion itself, because the contributions for the moment is there from the other part also, but just let's see the middle portion. It is like 3 3 is 9, and it is acting like 1 plus 1.5, that is 2.5 from A. So 9 into 2.5, that itself gives me 22.5. So I think you guys need to check this one more properly. Okay, so I think answer should be 30.83. Better look this up. Okay, so none of this is correct. Correct answer is this 14.5 and 30.83. Okay. Oh. Okay. Now, so this kind of gives a solution for all the questions of the assignment number 7. Now, let's quickly do some questions relevant to this assignment, because that might help you all just for the final exam also. You might get like idea to some the questions also. So let's see. So question number 13. If the bending moment diagram of a simply supported beam is a cubic curve with the span of the beam as its base, then the loading is. Okay. So the question is the bending moment diagram of a simply supported beam is a cubic curve. So we need to find like what kind of loading is there in the system. So for a point load, uh, for a point load in a simply supported beam, it's a linear case. So option A is wrong. Uniformly distributed load over the entire span, because this is linear. Okay, this is also wrong because it's quadratic or parabolic. Uniformly distributed load with a concentrated load at the span. So this would be kind of a parabolic, and there would be sudden shift in the uh, uh, like it would be mix of parabolic and cubic. So kind of it would be quadratic only. Uniformly varying load over the entire span. So this is the correct one. Correct answer is option D. Okay. Moving on to the next question. A 2-meter long cantilever beam is subjected to a 10 kilonewton point load at its free end. What will be the shape of its bending moment diagram? Let's draw this quickly. So there's a cantilever beam with 2-meter length. 10 kilonewton load is acting at the free end. So bending moment diagram uh, it would be kind of mm, yeah. So at this end it would be 0, at this end it would be 20, because the moment at x is 10x. If I take this as x, or rather minus 10x, so minus 20 kilonewton meter. The answer is option A, rectangular. A 2-meter long cantilever beam is subjected to a 10 kilonewton point load at its free end. What am I doing? Correct answer is option B, triangular. Yeah. Now, moving on to the next question. In a cantilever beam of span L carrying a uniformly distributed load W kilonewton per meter throughout the span, the maximum shear force is. So let us draw this first. A cantilever beam of span L is carrying a uniformly distributed load W kilonewton per meter throughout the span. Maximum shear force is. Okay, so if you let us draw the shear force diagram. I'll just write it here as bending moment diagram, otherwise I'll confuse. So shear force diagram. Okay, down. Uh, it's a UDL, right? Yeah. So shear force at any section X, it would be Wx or minus Wx. So this would be kind of this, and this would be WL. Okay, at any section it's a Wx. Okay, then this implies the maximum shear force would be this. Okay, answer is option B, WL. Mm, okay. Question number 16. For the figure shown below, the shear force and bending moment at a section 3 meters from the left support AR. So it's quite similar to what we discussed earlier. Just the values are different. Here the first value given is 5 kilonewton, and here the transverse load is acting as 10 kilonewton. So if you remember, we uh, we just found this reaction RB and try to compute the reaction 3 meters from here. That uh, if I say if I would just say this as section E, So we just need to find the shear force at E and moment at E. So for this, as I told earlier, I'll just take moment about A equal to 0. This would give me 5 into 1 plus RB into 5 minus 10 into 6 equal to 0, and this would be equal to RB into 5. 10 is 60 minus 5, that would be 55, and this would give me RB as 11 kilonewton. To calculate shear force and bending moment at a section 3 meter from the left support, so VE is would be equal to kind of RB, so kind of 10 minus RB, 10 minus 11, that is minus 1 kilonewton, and moment at E would be kind of 10 into 3 minus RB into 2, and this would be equal to 30, 11 into 2, 30 minus 22, 8 kilonewton meter. Okay. So if you see all the options, option A matches the best. The correct answer would be option A. Moving on to the next question. Question asks, we need to find the shear force and bending moment at the midpoint C of the simple beam AB shown below. Okay. So we can work around, and let us draw the SFT and BMD for this. So before we need to find the reaction force RA, RB, HA. Now taking sigma Fx is equal to 0, HA would be equal to 0. Now moment about B equal to 0 would be RA times 4 minus 6 into 3 and minus 2 into 2 into 1 equal to 0 would give me RA equal to, so 2 to the 4, 18, 4, 22 by 4. So this would be around 5.5 kilonewton, right? Now let's see. So if I want, what I want to have is shear force and bending moment at C. So EC would be RA minus 6. So 5.5 minus 6, this would be minus 0.5 kilonewton, and moment at C is RA into 2 minus 6 into 1. So 5.5 into 2 minus 6, it is 11 minus 6 is equal to 5 kilonewton meter. So minus 0.5 and 5 kilonewton meter, that would give me option C as the correct answer. Okay, now moving on to the next question. Now I hope you won't have any doubt in this. So moving on to the next question. Yeah, question number 18. In the figure shown, the bending moment M at the midpoint of the beam is. So we just need to find the bending moment at this, and let's say A, B, C. So we need to calculate MC. Okay, so for this, first thing first, let me draw the beam down below. There is this, and there's a roller. L right here, B here, B here. Capital P acting. The load is acting upwards here, downwards here. You want to calculate this C L by 2. Okay. Reactions. So R A, R B, because no HA would be there. So okay, so I'll take moment about B equal to 0. This would give me P into L by 2 plus L plus B, or let's see, R A into L minus B into L plus B equal to 0. This would give me R A is equal to P L plus B, or P B by L. No, rather I'll just keep this P L plus B by L. Now to find RB, do I need to? Not necessarily. So I can just directly compute moment at C. Okay, let me solve that also, so that if needed we can solve that also. So sigma Fi is equal to 0. That would be kind of Ra is positive and Rb is positive. Then there is one P upwards and there is one P downwards. So this becomes equal to 0. The Rb would be equal to minus Ra, and that is P L plus B by L. Okay, now let's find the bending moment at the midpoint of the beam. So moment at C is equal to, now I'll just follow from the left hand side. So moment at C, first contribution of the bending moment would be due to this load P, and that would be P into L by 2 plus B, and this is like take the negative side, minus B plus L by 2, because it's anti-clockwise. The contribution would be kind of anti-clockwise. Now due to RA, RA into L by 2. Now let's calculate this. PB minus PL by 2. RA is PL plus B by L into L by 2. That is minus PL minus, oh, this is PB minus PL by 2. P by 2, LL cancels, L plus B. minus PB minus PL by 2 plus PL by 2 plus PB by 2. So you see this cancel out. The remaining would be moment at C would be minus PB by 2. Did I make a mistake somewhere? Let me check. Let me see. Yeah. Okay, let me see. Into L by 2 midpoint. So if I take moment about B equal to 0, moment about B equal to 0, RA times L and P times L plus B. So P times L plus B by L. Yeah. That is my RA, RB, it doesn't matter. Okay. Now moment at C, the bending moment, M at the midpoint of the beam. That is C would be P times B plus L by 2. P times B plus L by 2. Then RA times L by 2. Yeah. RA times L by 2. Yes. Now RA is PL plus B by L. Yes. Where am I making mistake? Minus PB minus PL by 2 plus L by 2, L by 2, P by 2, P by 2, L and PB by 2. I don't know. Moment should come out as PB by 2. Okay, I made a mistake. Here, got it. So, what did I made a mistake is here. So I haven't taken the contribution of this load P, this load P. So it would be kind of minus PB equal to 0. So it would be kind of plus PB by L implies RA would be P L plus 2B by L. So this would be also 2B by L, 2B, no, this is B, this would be 2B, 2B, so this would be kind of PB, thus this would come out to be 0. So correct answer is option D, 0. Yeah, okay. Moving on to the next question. Okay, this is a very good question. quite an interesting question. So please have a look there on this. So the question is 100 Newton force is applied to the bow string of the bow. The bending moment at midpoint of the bow D is in Newton meter. So okay, so you can see in the figure there's a 100 Newton force is applied in this string, right? Like along this bowstring in order to release the arrow. So and we need to calculate the bending moment at this point of the bow D. So to solve this, okay, so to solve this, first we need to find what is the tension in the string of this bow. Okay, so taking at point A, you can see the horizontal force 100 Newton is acting like this. Now tension T would be there in the string. So tension T, both are equal, so I'll just draw this T and acting at 65 degree. Okay, now if we like resolve this in the component ways, or rather I'll just say sigma fx is equal to 0, kind of we'll get 2t cos 65 is equal to 100 Newton, implies t is 50 upon cos 65. Let it be like this as of now. T is cos 65. Now now let us take the section of the bow itself. That would be kind of this, like this. Okay. Now since tension T is there, here the tension T would be around like this. Okay. Now tension T is there, tension T is here, and if I resolve it in the component wise, this would be 65, so t cos 65, t sin 65, t sin 65, t cos 65. This is the point B, this is D, this is C. Distance is 350, and here the total distance is 1650. Yeah. Now we want to calculate bending moment at midpoint of the bow. So suppose BDC is my beam. Take it. Suppose that BDC is my beam and I want to calculate the bending moment at D. I know the reaction at the B. That so so let us calculate the bending moment at D. Moment at D starting from B. Okay, will be going from this direction. So kind of uh, so the contribution would be from T cos 65, the first thing, T sin 65, T sin 65 would be giving contribution with a 350 mm distance plus this t cos 65 and with a distance of if you see distance of 1650 by 2. So this is what we need to find, what we need to calculate. Let's substitute the t. So it's 50 by cos 65, 50 by cos 65 into sin 65 into 350 plus 50 by cos 65 into 1650 by 2 and units Newton mm. Okay, as of now the units are in Newton mm. Yeah, so this can be written as 50 into 0.35 into tan 65 plus 25 into 1.65. Now this would be in Newton meter. Okay, now let's solve this and that will give us the answer. So tan 65 into 50 into 0.35 plus 25 into 1.65. So this comes around 78.77 Newton meter. Let's see the option. 78.0. Option D matches perfectly. So please look this question closely because this is a very good question. If you feel any doubt, you can like ping to me or write it in the discussion forum, or you may ask us in the next discussion session also. Okay, moving on to the next question. I will skip this question because this is quite a similar question as we discussed earlier. Okay, moving on to the next question. Yeah. So this question, which of the following is the correct bending moment diagram for the transversely loaded beam AB shown in the figure? So okay, first thing first, let's draw the structure itself. The system is, we are given with a simply supported beam M and 2M, right? Yeah. So L by 3, L by 3, L by 3. A here, B here. Now reactions would be RA, RB. Let us find these reactions. So take a moment about B equal to 0. This would give me RA into L plus M plus 2M equal to 0 because all are in the same direction. This would give me RA as equal to 2M 3M minus 3M by L, and if I take Fy equal to 0, Ra plus Rb equal to 0, that implies Rb should be equal to minus Ra, and that is 3M by L. Yeah, okay. Now to draw the bending moment diagram. the bending moment diagram, starting from the left, it's 3m by L into x, right? It's a linear variation. 3m by L into x. So yeah, 3m by L x. So at a distance L by 3, it would be equal to minus m. So it would be kind of this at L by 3 minus m. Then there's a shift in the minus m plus m. So moment will go to 0. Then moment will go to 0. Then again there's again contribution minus 3m plus L. There is a contribution from RA is still there. So till L by 3 again it will be kind of this. Now due to 2m it will shift towards the positive side, and that would also be equal to m. Then again due to RA it will go towards 0. So this is m, and this is A, B, L by 3, L by 3, L by 3. So that the correct answer would be option C. Okay. Now moving on to the next question. Moving on to the next question. Question is a 10-meter long simply supported beam carries a UDL of 10 kN throughout its length. Counterclockwise moment of 60 kN and 40 kN applied to the two ends of the beam at the supports. Draw BMD of the beam. Okay. So okay. So this is like the last question of the today's session. So let's solve this. Okay, let's draw the beam first here. So we are given with a simply supported beam. With a UDL of 10 kN. 10 kN per meter. Length is 10 meter. I'll take this as A, this as B. A, B, and moments. So to reiterate once again this last question. So the 10-meter long simply supported beam carries a UDL of 10 kN per meter throughout its length. Counterclockwise moment of 60 kN and 40 kN are applied to the two ends of the beam at the support. We had to draw BMD of the diagram. For this, we first calculated the reaction support reactions, and HA was directly equal to 0 using the summation of Fx is equal to 0. Then by taking moment about B equal to 0, we were able to compute RA, and then taking summation of forces in the vertical direction, that gave me the reaction support RB, that is equal to 40 kN. Then to calculate the bending moment diagram, we started from the left hand side. So at the immediate left, the leftmost, there won't be any contribution from the reactions or the UDL. The reaction, the contribution would be from the concentrated moment, and that would take me to the minus 60. So as further we move, the moment at any section x would be minus 60 plus 60x minus 10x square by 2. So I took this mx, and say first thing is that this would be in this is quadratic in nature, so the curve would be quadratic, that is for sure. Now we can see that at certain point x this would become 0, so you try to find like where the bending moment would come out to be 0. So taking this moment expression, minus 5 is x square plus 60x minus 60 is equal to 0, we were able to find the distance from A where the moment is coming out to be 0, and that is like 1.1. The other value was coming out to be 10.89, that is like greater than the span of the beam itself, so that is not the correct one. So 1.1 we can see, so this trend will follow then the quadratic nature, and till the support B there would be some values, then due to the concentrated moment at B, this will again make it to 0. So like if I may, just to the left of uh, B, just to the left of B, it would be kind of minus 60 plus 60 into 10 minus 10 into 10 square by 2. This would be equal to minus 60 plus 600 minus uh, 500, 600 minus 100, this is equal to 40, right? So at the rightmost end it would be 40, and due to the concentrated moment then again it will shift back to 0. Okay, so this is it for this question, and this wraps up our today's discussion session. I hope nobody has any doubt. You guys can like look up the video and the notes, and if you feel any doubt you can post it in the discussion forum, or you may ask it in the later discussion sessions also if you uh, feel like it. Okay, so this is it for today's discussion session. uh, so to tell you one more thing is the next discussion session would be on 19th, because the last discussion session was postponed. So so next discussion session will happen on 19th, same time, 4 to 6 p.m. Okay, this is it. So we'll wrap up the discussion session. Thank you all for joining. See you on 19th, same time, 4 to 6 p.m. Bye, take care.